there are some variations of this reaction. So, the simple variation is in your halogen group, that can equal bromine, chlorine, or iodine. And then in your nucleophilic solvent, there's a lot of variation here. What you need is something with a ZH bond. So what is that? Well, the R that I put, that can just be a hydrogen or carbon group. The Z needs to have at least one lone pair, and it should be a heteroatom, something like nitrogen, oxygen, or sulfur. And then, of course, it has to have the hydrogen, because that hydrogen gets taken away in the final step. So let's tackle a problem like this. Here we have the alkene. We're reacting it with iodine and this amine. Again, we have the nitrogen with a lone pair. It has a hydrogen and some carbon group attached. So what you can go ahead and say about this is, if you work through the whole mechanism, and I encourage you to do that, the nitrogen will end up adding, and it will keep all of these carbons. It'll also keep one of its hydrogens. One hydrogen is lost in the final step, the same way a hydrogen from water was lost in the final step in the mechanism we did previously. So one thing you can do is go ahead and start by just drawing the product. I'm going to go from the alkene to the alkane. The halogen adds to the less substituted carbon. So I'll put the I there. The nucleophilic solvent adds to the more substituted carbon. What we need to draw a bond. That bond goes to the heteroatom, the nitrogen. And that nitrogen will have the hydrogen and the 3-carbon chain, like that. Now we can deal with the stereochemistry. Now we know that the I and the nucleophilic solvent add trans, but we only have one chiral center in this molecule to deal with. So let's draw this how you might do it. And you might put this and put the I on a wedge and the amine on a dash, and then do the opposite and put the I on a dash and the amine on a wedge. But you'll notice if I were to draw this product and say an answer key, I wouldn't be putting this I on a dash or wedge because it's not a chiral center that I need to define. This is my chiral center here. So when I draw this, we really don't need to put that dash or wedge for the I group. So a better way to draw this has the I as just a straight bond, and then I'll still put the amine as a dash. And then the bottom one, again, I'll put the I as a straight bond and the amine as a wedge. It's not to say that this representation is incorrect. It's just unconventional and unnecessary to put a dash or wedge at this carbon that's not a chiral center. So then we can see that the two products here are enantiomers. Here's one final example that I want to use to show you just how to deal with the stereochemistry when you have this flat alkene structure and what to pick as your end-plane groups and then your dashes and wedges. So first, figure out what you want to keep in the plane. Well, you have to keep the alkene in the plane. And from there, let's just highlight the rest of a chain. Let's keep this in the plane. And then it's totally acceptable to pick the phenyl here to keep in the plane, which means your ethyl will end up as a dash or a wedge. Or we can do the ethyl group in the plane and put the phenyl as a dash or a wedge. Both will give you correct products. It doesn't matter. You just need to pick something and then be consistent. Once we've done that, let's draw our chloronium ion intermediate, and it will come in from the front and the back, so we'll put it on wedge groups and dash groups. So what I've done, I've drawn my base structure twice. I've gotten rid of the alkene. Then I'm going to put the chloronium ion as a dash group, going back, and as a wedge group coming out. From here, you can go ahead and give the phenyl group stereochemistry, putting this back and this out. I'm just going to wait and deal with its stereochemistry in the end. So next, let's add our nucleophile, which is ethanol. We know from our previous discussion that the ethanol will add to the most substituted carbon, which is going to be this carbon. And in the first case, because the chloronium ion is back, the ethanol is going to come in from the front. In the second one, because the chloronium ion is out in the front, the ethanol will add from the back. So then to draw the product of this step, go ahead and write your main chain, the one I've highlighted in red. That's going to stay in the plane no matter what. So let's keep it highlighted. Now, we know that on this carbon right here, that ethanol is added, and it adds from the front side. So let's put it on a wedge. We have the OH, the ethyl group, and a positive charge. And since we have two things in the plane, one is a wedge, the fourth group, the phenyl, must end up as a dash. And that's because as the ethanol comes in from the front side, it pushes that phenyl to the back. Then the chlorine opens up, and we get the chlorine added here in the back. Do the same thing with our second molecule. Again, keep the chain that you highlighted in the plane, don't affect it. Then in this case, the ethanol adds to the back, so let's put it on a dash. And that means the phenyl will be out. And then the chlorine will be out on the other side. So now the final step, and don't forget we need a second arrow here on that chloronium ion. The final step, we just need to get rid of the proton from the oxygen. And I like to keep it simple and just use a B with a lone pair. That will come over and take away the proton. Once you do that, you just lose that hydrogen from the structure, so now you have the O-ethyl group with no charge. These are your two products, and in this case we have two chiral centers, one here and one here. But between the two structures, both chiral centers are inverted, so that means we have a pair of enantiomers.